school, my computer's dead, I ripped my contact. My dog's crying.
This is one bad day. Well, hey, at least get some math. All right, so here we go. All right, do we feel good about expressions and equations?
Yeah.
Feel good about it? Okay. Just make sure that you're comfortable with substitutions. The basic computations you're going to have to do in your homework today is just taking numbers and plugging them in. I don't really need to go through it too much, but I just want to make sure that you're comfortable with a problem like this. This is something we're going to talk about today. This is the type of problem that we didn't get to yesterday. It was at the bottom of the list where I want to go through the properties. But this is an expression, right? There's no equal sign. That was what we started with yesterday. We were talking about that. What they're going to do for you today, they're going to give you a problem like this for, I think, the first 3 problems, something like that, the first 3 out of your 10, where they're going to tell you an x and y, you plug it in, you solve it. You simplify it down to a single number. It's pretty straightforward. You don't need to show all the steps, just show a couple. So I'm not, you're not just hitting enter on a calculator. Like, actually try to do it, without a calculator if you possibly can. So maybe they'll say like x is 10 and y is a 1. Plug them in, solve it out. Okay. But again, we'll go through the steps today, the order of operations. I know it seems silly, but it is nice to review that to make sure that you're going in the right order and you know what to do. Because there's different ways to do that problem, but we'll talk about it. But we'll get to that. That's our new thing that I want to cover today. So we did expressions. The big thing about the expression is there's exponential form, where they have exponents. That's one of the properties that we talked about yesterday. What about intersections and unions? Do we understand the differences? Intersections, what they overlap. Union is when you add all the answers together, all the terms. Okay. The one thing that they are going to ask you for in one of the problems I assigned was to look at a problem and tell me what the intersection and union is. Now we're going to talk about with a graph, because that's something we're going to be eventually going into, but your homework's going to be a lot easier than what I'm about to show you here. But it'll be something like this. This is a problem I did something, I think I did one of these yesterday. Okay, it's a problem like that. Okay. You have 2 sets, that's roster method. They should be least to greatest in both sets. If they're not, we'll put them in there. Sometimes they can put variables in there. I know that seems a little weird. If they're going to put variables in those little curly braces, just put them in alphabetical order. That's what I would say. But anyways, numbers, numerical order. This symbol, what does that stand for?
Union.
Union. That means you just add. Union is you combine everyone together. So on this case, you just put them 1, 2, 3, 4, 5, 7, and 10. Did I skip any numbers? I don't think I did. Even if there's repeating numbers, just list it once. You don't need to put 2 of them in there. It's just all the numbers combined in order, least to greatest. Now, the difference here, so that would be a union. If they wanted an intersection, it'd be a little n. Now they're trying to figure out what numbers do they have in common. Well, if you're looking at that list, you're like, they don't share anything. Fine. This is the symbol we talked about yesterday. That's the empty set, the null set. They don't share anything, boom, that's what you put. They don't have anything in common. They have 1, put 1 number. It's fine, it doesn't matter. They have multiple sets of numbers, fine, do that. But just make sure you list them. Okay, do we understand the difference between intersection and union? Feel a little bit better? Now, I think the last thing we were finishing with yesterday, perfect. What we were finishing with yesterday was what happens if you have a graph and you're trying to look at the intersection and unions on graphs. That was something that I wanted to talk about. That can be a little more intense because now you're looking at either domain or range and you're trying to put all the different parts together. This is what you're going to have in your homework today. Yeah, just put it like this. Thanks, Art. That's the homework problems. But what I want you to get familiar with is like what we're going to use this stuff for, because it seems a little silly, like kind of pointless. Like you're like, I don't understand why we'd ever do something like that. It's for graphs. You're listing off a domain. You're listing off a range. Domain is like the numbers you're allowed to use. It's the input. It's what they call the independent variable, the thing you're in control of in an experiment. So on a graph, it'd be like the x numbers, the x-intercepts. Okay. So let's say we did something like this. Let's just make that a closed circle, make it easier. Okay, what you're looking at here, this is a piecewise function. It's multiple pieces. It's not continuous. It's not flowing. There's actual breaks in the graph. But the idea is that it is still a function. Why it's a function in math is that for every x number, I guess for certain x numbers, there's only one output coming out. There's only one y number. It's not like there's an overlap, because there is a gap right here. There's a gap between here, so there's no overlapping. So that does make it a function. For every input, there's one output number coming out. The best way I can say it, like what wouldn't be a function is if you're graphing and you had, if you had something like this. This is what the graph looked like. Now we have a problem. It's not a function. That you couldn't. There's this type of problem. If you were to have like an equation that represents that, which is something we're going to learn this year, you couldn't just type that problem in a calculator and get it to solve for a certain answer, right? If you were to type in 1 into your calculator, maybe the 1's right here, it would have a problem because there would be two outputs. Your calculator would say error or domain error because it doesn't make that choice of which answer it should tell you, the top one or the bottom one. So it's not a function to begin with. Now don't get me wrong, there is solutions to the number 1, but there's two of them and your calculators can't handle it, especially like these. Now those upper level calculators, the ones that like the TI-89s and TI-84s, they could handle that. They could tell you both answers, positive and negative numbers, because they're programmed to do that. But it's still not a function. This one is, even though there's bricks, it's just, it's known as not continuous. It's not flowing from left to right. But what I'm going to ask you for, especially with like this intersection and union stuff, would be tell me the domain, the x numbers. So on this side, from like, because there's a break. So in fact, let me use a different color. So over here, there is a chunk of x numbers, correct, that I can use. Now, what is the lowest x number going this way that I can possibly use?
Negative infinity.
Negative infinity, right? Because it has an arrow, so it's going this way forever. It doesn't stop. So the lowest x number I'm going to be eventually going towards is negative infinity. Now, negative infinity is not a number, it's a direction. That. And then I'm going to eventually move up until I hit, what is this, negative 4? So that would be the domain set, because negative 4 is right where that dot sits, and it's a solid dot. So how that would look with intersection and unions, we would have to go to interval notation.
Did you teach yourself to write left-handed?
No. I am left-handed. Never noticed. Never noticed that left-handed? No. Most people don't. I don't understand. Interval notation. Do we remember that from yesterday? Okay, that's where we have brackets or parentheses. Okay. So, going from the left side to the right side, we're going to start with negative infinity. We have to use a parenthesis. Anytime you use infinity symbols, you have to use a parenthesis. It's not included. It's a direction. So you're going least to greatest. So I'm working my way up until negative 4, right? That's when there's going to be a break in the graph. Now, at negative 4, is that a solid or open dot?
Solid.
Solid. Put a bracket. It's included, solid dot. Now there's going to be a break in the graph, right? Because there's a break. There's a break from here to about here. So now, since it's not flowing continuous, we're going to do a union with the next part. So we're adding it to the next section of x numbers I'm using. Again, I'm using x numbers, not the y numbers. So, what is this number right here?
Negative 3.
Negative 3. Included or not included? It's included, right? It's a solid dot. So you're going to have a bracket, negative 3. We use the brackets when it's a solid dot. If it's an open circle, you use a parenthesis. Or if it's an infinity. So then we're going to go up. Well, if we keep going up on the x numbers, it looks like, what is that, 3? And we're going to have another bracket. And then, because it stopped again, because there's a break in the graph. It's not flowing continuous. And now we're going past that. It looks like it's going to go from, what is that, 4 and up. Now, I'm going to do another union. I'm running out of space here. But I'm going to do another union. And now when I start at 4, what do I have to make sure of?
So parentheses.
Parentheses, right? Because you can't include it. It's an open circle. So it's just past the number 4. And I'm going towards what? Positive infinity. And I'll need to use a parenthesis again. This is a perfect use of unions and intersections. I think it's the easiest way to list off all domain numbers. It's the fastest use of it. Okay, that's the purpose that we have this stuff for. I like interval notation like a lot. It's really clean, it's really quick. As long as you know those basic rules. Least to greatest, left to right, And just make sure you know when to use a bracket or parenthesis, and make sure that you're very clear on which one you're picking. If there's any wiggle room, like you don't know what that symbol is, usually I count them, because I don't know which one it is. Okay, questions at all about that? Okay, here's what I'd like you to do. I would like you to try to tell me the interval notation for the range now on your paper. Try your best. Range are Y numbers only. So the range, Y numbers. Now I'll put some numbers up on this list here, just so you know. So again, we're using the Y numbers for the range. So let's go here. So this is -1, -2, -3, -4, -5, -6, -7, -9. Alright. See if you guys can figure out the range now. Same structure, you're still going to do interval notation, but you're giving me the Y numbers now. So the range. This is one of those parts I want you to try. Even if you get it wrong, it's fun to try. I know this is not one of those major things I'm going to be doing in the homework today, but it is something that is intensely important later on for the later sections. So that's why I'm practicing it now, because this stuff was just introduced in this section, but they don't really discuss it after it until we need it. So I want to make sure we get some practice with this stuff. This stuff is usually the most difficult stuff for my first test. Stuff people always make mistakes on. Okay. Looks like everyone's kind of done writing. Do I have a brave volunteer that would like to come up here and try to write it on the board? Anyone? Give it a shot. You can even have discussions and say, hey, do this, change this. Okay, let's get one person to walk up here.
Oh,
Yes!
okay.
Okay, here we go.
Don't make fun of me because it's
No,
wrong.
no. We're here to learn.
Okay. So.
Nice. Any problems with anything she wrote there? Anyone have something different or something that you don't agree with? Good, because it's correct.
I was gonna say she wrote in blue marker.
She wrote in blue. Yeah. But it is correct. It is correct. Everything was perfect. She started with the least, the smallest number, the smallest Y number, and she had a bracket because it was included, right? -7 on the Y numbers was included. There was a solid top there. She worked her way up until she got to -1. Perfect. Had a bracket there. Had a union. Started at 1. Now, this is the part that people would have a problem with, right? Well, that one's solid, that one's open. Which one do you pick? Well, it's solid. It's taken. There is a number there at 1, okay, for the range. And then you worked your way up and went to infinity and used parentheses. And I love the fact you put the plus in front of the infinity symbol, right? Pos infinity. It's important to put that there. Okay? Very nicely done. Okay? Now, that's all fine and dandy. Now, where would you use an intersection? Intersections is where there's overlap in the graph. So if they wanted to know say we're using the range still, let's talk about the range. Well, let's say these are 3 different functions, right? Because it's piecewise. There's 3 different things going on here. Is there intersections of the range numbers? Is there overlap on the range? And where would that be? Where's the overlap at? 1 and? Yeah, 1 and up, right? That's where the overlap is. So on the range, where there's an intersection, on the range, it's from 1, and we would not include it because one side has it, one side doesn't. So there's no overlap at 1, but just above 1, towards positive infinity, there is. This would be the intersection of the range if you're looking at 3 different functions. There's an overlap there for the range. Now, why I bring this up is because you could write this technically differently. Instead of writing it like that, even though it's correct, you're starting at 1 and going up towards infinity, and that's kind of where the overlap is. It could be this. One side had 1 and went to positive infinity. And we're going to do an intersection with the other one that was from 1 to positive infinity. You're looking at the intersection of 2 different intervals. Not a union, but an intersection. So when you look at both of these, and you're like, okay, here's one interval, here's another interval, and we're doing an intersection of it, this is the answer. That's the shortcut for writing it. Most people can see it common sense. You look at the picture and go, okay, there's an overlap from 1 and up. Okay? This is what I would expect to see. But you could write like this because you can use those symbols. You can see where there's overlap on it. Does that make sense, like why you could do it 2 different ways? I like the top one. The top one, the one I circled, is pretty much the way everyone would probably think about it. But interval notation is super easy once you get it figured out. Okay. We good? Does anyone need another example of it? You're not quite getting it. I know like that bottom part's kind of goofy, but because it doesn't look like it's going the least to greatest. Because we're doing intersections, so you're trying to find overlaps. Okay, nice. Okay, let's move on. Let's talk about absolute value. Then we get to our topics here. Da-da. Okay, absolute value. This is the absolute value symbols. They're big italicized bars. You can usually put numbers on the inside, like such. Absolute value negative 3. 3. Okay. Absolute value 10. 10. What's the rule?
It's always positive.
Always positive. That's a rule. What else?
How far from 0 is it?
Exactly. On a number line, how far from 0 are you? It's a distance. That's all this is. Absolute value is a big fancy way of saying find the distance on a number line. So if you started at 0, so here's a number line, and you start at 0, how many bunny leaps would it take you to get to negative 3? It would take you 3 bunny leaps. Because taking steps doesn't matter if you go forward or backwards. Like if you had a pedometer, or if you had a smartwatch, and you're tracking your steps, right? It doesn't matter if you go forward or backwards, it's still a step, and it's still going to mark it. So that's the whole purpose of absolute value. Now, there's properties with absolute value, things that people don't know, that they don't realize. Like for instance, if we were multiplying 2 numbers on the inside of an absolute value bar, 2 numbers, doesn't matter what your numbers are, I picked X and Y, but there can be any numbers you want. That's the same, this is exactly equal to, if you were to separate them and multiply them anyway. Like have their own absolute value and multiply them. Because it's going to be positive anyways in the long run. It doesn't matter. Because whatever these numbers are, one could be positive, one could be negative, whatever it is, you're going to take the absolute value bar of it. Fine. And if you separate them, they'll still turn out to be positive, you're going to multiply positive numbers, and it's still going to be positive. It'll be the same digit anyway. It works for division. In a division bar, where you're dividing 2 numbers, whatever it is, 10 divided by 5, and you could separate them into their own. That's still a basic property of absolute value. Where it differs, you can't do it with adding and subtracting. That's a huge deal. That's something people get wrong when they go from Algebra 2 to PreCalc or to Calc. They forget that they have it's called the product rule and the quotient rule, but they don't have it for addition and subtraction. No sum and difference rule. Because if you try to do it, where you're like, okay, I'm going to add 2 numbers together, that's going to be equal to them separated. That's not true in certain cases. Could be in certain numbers, but these don't work. That's not always true. What's going to happen, what you're going to find, is that this is the case. They could be equal in certain cases where you only use positive numbers, but typically the left side, when I have the x plus y inside the absolute value bars, that'll be typically smaller than the other side in most cases. Because if I were to pick a negative number and a positive number, this will turn out to be what, the number 1. And if I put them over here, this will turn out to be 3. 1 plus 2. So the left side typically turns out to be smaller. What this is called the triangle inequality. This is actually how you prove if you had 3 numbers, if you have a triangle or not. This is something people don't realize on like an ACT when you're taking it. Like if they're trying to say, hey, is this a triangle or not? Or you're looking at a picture of a triangle and they have something like this. That's not a triangle. It's not a triangle. It's actually a stick, and they drew it wrong. Because the only way you could go around the block and go take the shortcut home and still take the same number of steps is if it's the same path, where this is 1 and this is 3, and you walked 4 home. It's not a triangle. Any 2 walls you add on a triangle should always be more than the 3rd wall. So what should happen here should be something like this. Now that's a triangle. Because 2 walls will always add to be more than the 3rd wall. Going around the block should be more steps than somebody taking the shortcut home. Every single time, because of that. Distances. 2 distances added together should always be more than the 3rd wall. Or the 3rd walls. And if they're equal, because there's that rare case where they're equal, it's not a triangle, it's a stick. Okay, questions with absolute value. I know that I just threw that out there because it's kind of weird. Because if you don't know, the graph that I have on the board is just 2 number lines, just overlapping. That's all it is. Really, the grid isn't there. It's just because of the number lines, they extended the markers for number line. And the number line basically comes from absolute value, and that's what we talked about. Now, why would we ever do that? There's a way to find distance on a graph. That's something we're eventually going to go into. How do you find distance on here? Well, I'll show you the formula. We'll talk about where it comes from. But there's also distance for a number line. Like, how do you find it? So, to find distance on a number line. So this is by far the easiest way to find distance. When you have 2 numbers that are in a straight line with each other. So let's say this is 0. Here's 4, and let's go down to -2. Right? We're going to find the distance from here to here. How many steps are we doing? You can calculate yours. Figure out it's 6. All right, whatever. But how you do it? You can pick any of the 2 numbers, any order. Just call one x, the other one y. You subtract them from each other, and you put an absolute value bar around it. You subtract them and put an absolute value bar. It'll tell you the distance between them every single time. And it doesn't matter the order you put them. So I could have laid that one y, that one x. -2 minus 4. Put an absolute value bar. That turns out to be -6. The absolute value of -6 is 6. There's 6 steps in between. Works every single time. That's why we have absolute value. Let's find distance.
So if it was another negative number, it would be positive.
So if maybe I went from, I'll just pick this, right? Let's go from -3 to -2, right? Because you know it's going to be 1 step, right? So -3 minus -2. Because you always subtract no matter what the numbers are. The number's negative and the other number's negative. You always subtract them, whatever they are, because that's the way the formula says. This will turn out to be +2, because negative, negative make positive. That turns out to be -1, and 1. Works every time. As long as you subtract whatever the 2 numbers are, positive or negative, doesn't matter, you subtract them. Again, there is more formulas than that, but we're not to those sections yet, where we talk about distance when you tilt the line, not in a straight line, not collinear with each other. Okay, now we got to talk about the properties of algebra. So we get to that one problem that I put up on the board earlier today. All this stuff is little minor review stuff. Maybe you didn't remember this, or maybe you never saw that before.
So does it matter what order you put them in for that?
No, not at all. You can put them in any order, subtract, the absolute value bars works every single time. Very sustainable. All right, let me start the camera here, and then we'll get going on these next properties. Okay, so the basic properties of real numbers. Now I'm going to list off a couple of properties here. Okay, so these are the properties that you probably should have learned in either geometry or algebra 2, maybe even algebra 1, maybe. Okay, first one, and we had a different name in our geometry textbooks, but one of the major properties in algebra is called substitution. Now, am I going to have you write all these properties down and work? No, I'm not. This isn't geometry class. Right? Substitution. Anytime you do random arithmetic, 5 plus 2, 10 divided by 5, 16 minus 4, just random arithmetic. That's substitution. We have other properties. We have like commutative property. The commutative property is when you move things around. You're allowed to do that. You're allowed to do that with adding or multiplying. So if you had a bunch of problems like this, it's easier if you move them around to group. So because they're all being added, so you can like switch. I can go the 6 plus 4 and the 7 plus 3, like move them so that I get 20 really fast instead of going, okay, 4 plus 7 is 11, plus 6 is 17, plus 3 is 20. That takes too long. Group, move things around. You're allowed to do that for addition or multiplying. Let's see, 4 times 3 times 5 times 2. You can move things around. Because maybe you want to go the 5 times 4 route, get 20, and the 6 times 3 route, which is 6. And did I say 6? 3 times 2, so you get 6, so 20 times 6, 120. Instead of going, okay, 4 times 3 is 12, times 5 is 60, times 2 is 120. Like, it takes too long. Group it, move it around. Okay, that's commutative. Do we use commutative a lot? Not really. The other properties we have associative. Associative property is just when you move a parenthesis around. Like if I had something like this. I can move it so I can take the 5 times 2 first, then times 7.
May I have your attention, please? We have 2 cars that have their lights on. One is in the west parking lot. It's a gray Honda Civic, license plate GG415. Again, that one's in the west parking lot, a gray Honda Civic. In the east parking lot, we have a red Chrysler Sebring that have lights on as well. We do not have a license plate number on that one.
You can just put it.
Oh, okay.
Put it back there, I'll grab it here in a minute. Right in that little tray if you want. Yeah, right there. Perfect. Okay. But this is associative property, right? You can move the parenthesis around, you can get to easier way to do that. Instead of going, okay, 5 times 7 is 35, and then you're trying to take times 2, maybe you don't even know how to do that, but 70 anyway. But I gotta go 2 times 5. Because it's the same thing as this. Instead of just rearranging, you can move the parenthesis and do other things first. Now I know that seems weird, because I always get this one person that comes from algebra 2 and they're like, Ward, can you just distribute? Just distribute that through? No. When's the only time you can distribute numbers over a parenthesis? Anyone happen to know that rule? When can you actually take the 2 and multiply it through?
When it's addition and subtraction.
Exactly. When it's addition or subtraction, now you can distribute. That's the only time you can choose. Now, do you have to distribute? No. Maybe you just want to go, this is the 12 route, take it times 2. You get 24. Maybe you just want to do that, because if you're capable of adding those, add them. But if you want to distribute 2 times 5 plus the 2 times 7, you could do that. Then you get the 10 plus the 14, you get 24 anyway. Now, the reason why they have this, because I've already said this next property, which is distribution. Why we have distribution. It's when you're multiplying numbers, usually over a parenthesis that has variables in algebraic expressions. Something like this. 3, 4x plus 11. Now you have to distribute, because you can't add the 4x and the 11 together. Because one has a variable, the other one doesn't. They're not like terms, so you have to distribute. But why they created distribution in the first place? This number. This example is why they have distribution in the first place. Because the easiest way to do this problem is to know that it's going to be 600, right? And then you're going to subtract 12 off of it. Here's how I know. 98. Do you agree that 98 is 100 minus 2? Okay, do you agree with that? 98 is 100 minus 2. Distribute over. That's why they created distribution. It's easier doing this math in your head than trying to take 98 times 6 and taking 600 minus 12. which is 588. Okay, because if you do this, this is 600 minus 12, which is 588. There's no way I would have gotten 588 from doing the top one. I can't do 98 times 6 in my head. I have to write it down. That's 48, carry the 4, that's 54 plus that. It's too hard. I can't do that in my head, right? I can do it when I write it on the marker board, but I can't do it in my head. The distribution way, I could. Potentially I could. That's why they have distribution. That's why they originally came up with it. Breaking numbers down. You don't have to always go hundreds. You can go any number, tens and whatever. Any questions with the basic properties? I know I just kind of give you a crash course. Now, the whole purpose of this was that first problem that I started with today. I said this is the type of problem, oh, I think I did x. X plus 5 plus y squared. And I think I put a 3 out here. This is the type of problem that I might throw at you in your homework today. You might have like 3 of these right in the beginning. Where they're going to tell you, okay, x is 2 and y is 1. And you have to plug them in and solve. Well, you have to know your order of operations, you have to know your properties. When can you distribute, when shouldn't you? So if I were to plug these numbers in, 2 plus 3 times 5 plus 1 squared. Well, if you have an algebraic expression, this is the order you have to follow. You have to follow that order. Because if you don't, if you go out of order, you'll get wrong, incorrect answers. So what I should do first, I should do anything inside the parenthesis first. So that should be the number 6. Now, I should do, so that's checked off, because once all the math in the inside of the parentheses is done, you can check it off. Now I'm going to do the exponent. Well, that's 36. 6 times 6, because squared means you have 2 of them. So that's 36 times 3. So that's checked off. Exponents are done. Now I can multiply 3 times 36. 8 carry 1, it's 108. Then you can add the 2, you get 110. But you gotta check these off. Now, the middle ground here and the back 2, it doesn't matter the order you put those. Multiply or divide, it's whatever comes first, left to right. And then add and subtract, same thing, whatever comes first, left to right. So if you had a problem like this, you should subtract going this way first. Don't do the back first. You'll get different answers sometimes. Questions, comments? Anything? Okay, homework today. I know that you're like, or you got like 5 minutes left of class. Yeah, but I'm going to give you a time in class because I like to give your homework. This assignment, I believe, is due Friday this week. Give me a couple days to work on it. We'll be eventually getting one more assignment this week, but this one's due on Friday at least. So it gives you some time. Okay, and I will put it over there. Okay. Page 15, numbers. 3, 9, 15, 21, 22, 29, 30, 93, and 96. And I don't like it, so that just jumps. Those are problems. Okay, there's 10 there. No, 9. I only have 9 problems. There you go. There's your homework. Due Friday. Should be easy. I'll give you some time in class tomorrow so you can ask questions if you have it. Now, what is also due tomorrow?
Your cover and book.
Book cover. You need a book cover. Now, I already see some of you have it. Perfect. Good work. You need a book cover. It's all or nothing tomorrow. It's 5 points or nothing. And I still make you put one on there. Get a book cover on there. If you need a bag, I'll give you a bag. But it has to be on the minute you walk in tomorrow. Not that, oh, we haven't attached it yet. It's got to be on when you walk in. Or at least before the bell goes off, it has to be on. So now some people can hear it early. Okay, we're good? Done for the day.